Hello and welcome to another IEEE Spectrum hands-on video, where this time we'll be doing a deep dive into one of our favorite kits, the 3.5's Discrete 555 Timer Kit. And who knows, this might be the start of a series exploring more kits, but for now, let's get stuck into this one. By the way, I'm Stephen Cass, the editor who has been responsible for Spectrum's hands-on column for, dear God, about the last 10 years. Or to put another way, back when people were black market trading in Raspberry Pi Model B Pluses instead of Pi 5s. Before we look at the kit though, let's look at this little guy. As you can see, this integrated circuit is about the size of a fingernail, and it's a 555 timer chip. If you're not an electronics engineer or a hardware hacker, that may not mean much to you, but it's not an exaggeration to say there's probably not an EE alive that hasn't used this chip at some point. It's a humble little thing with a ridiculous number of applications. So let's take a better look. There's 8 leads or pins coming out of the 555, which was actually really important to success the chip when it was launched in 1972 by Signetics. The first design of this chip needed 9 pins, which because of the standardized package sizes meant it would have to be put into a 14-pin package with 5 pins left unused. But the inventor, Hans Kaminzijn, performed some engineering magic and worked out how to get rid of 1 pin, meaning they could fit it into the more compact and cheaper 8-pin package. Now let's take a peek at the circuit inside in block form. The really critical parts are the circuit blocks in red: 3 resistors, 2 comparators, and a flip-flop. The 3 resistors are analog components that divide up the voltage being fed into the chip into 2 internal reference voltages at 2/3 and 1/3 the level of the original voltage. The 2 comparators compare the voltages coming into the chip at the trigger and threshold pins against these internal reference voltages and use them to control the operation of a flip-flop, which is a sub-circuit used in digital designs that can be set by a transient pulse to continuously output a high or low voltage signal. The surrounding circuitry that you connect to the control voltage, threshold, and trigger pins can radically alter how the chip operates, but one common use is a so-called astable oscillator mode, in which the 555's output flips between high and low or on and off like a metronome. This is an incredibly useful thing to do. Just a few examples. You can use it to blink a warning light on and off, measure how long some event takes, or by varying the frequency of the oscillator, synthesize musical tones. We'll do a live demo of how the 555 works in practice at the end of the video, but for now I just want you to appreciate that the 555 is really a hybrid analog digital chip, one that turns varying analog voltages into digital on and off signals. The design of the 555 chip is widely considered to be one of the most elegant circuits in engineering, but it's hard to really appreciate because, let's be honest, one little black box looks very much like any other little black box. This is where the Discrete Timer Kit comes in. It replicates the microscopic integrated circuitry inside the chip with human-scale discrete components. You can make your own 555 timer without a semiconductor fab. And you can even wire it into any project that uses a 555 timer. What's the point here? 1, it looks pretty cool and lets everyone know that when it comes to integrated circuits, you have taste. 2, you really come to appreciate the elegance of the design. Just a handful of transistors and resistors that make up the electronics equivalent of a Swiss Army knife. So here you can see the size of the kit compared to the original 555 integrated circuit. And this IC was created with transistors that would be considered enormous by the standards of today's latest processors. Building the kit is a pretty straightforward soldering job, following the general rule of soldering order, which is you start with the shortest components first, which in this case are the resistors, and then work up through the taller components. It's not so critical because I'm using this jig that lets me rotate the board, but it's still a good practice for those times when you have to flip the board over and lay it flat on its components on some surface. If you don't solder the short ones then, they'll slip away from the board. This kit was created by Eric Schlaepfer, who is also famous for his photographs of dissected electronic parts. Last year, Spectrum ran an excerpt from his amazing book, Open Circuits, which showcases the unfamiliar innards of familiar components. You really should check it out. We'll put a link to the description to that. Eric is also the creator of a discrete transistor version of the classic 6502 CPU that powered computers like the Apple II, Commodore 64, and BBC Micro. It's this beautiful monster that's about 30 centimeters by 38 centimeters inside with all these blinky LEDs, and you can actually wire it in to a complete computer. If you ever get a chance to see it, I highly recommend it. As you can see, I'm having a little difficulty keeping the 555 printed circuit board in the jig because it's much thicker than a regular PCB. Now, if you go forward, eventually you'll see when I'm about 80% done, I do finally figure out there's a wider notch I can put the PCB in if I turn those little holder things 90 degrees. Oh well, live and learn. These three 4.7 kilo ohm resistors I'm soldering in now form the internal voltage divider that provides the reference voltages for the comparators. Little insider gossip here. As you can see from the logo on the box, the kit was originally produced by Evil Mad Scientist Labs. This was a really great indie outfit on the West Coast that made a bunch of really cool products, including the AxiDraw series of plotters. It's an AxiDraw plotter, in fact, that we used to make the titles and diagrams for this video. The success of the AxiDraw line ultimately led to Evil Mad Scientist being bought earlier this year by Bantam Tools in Peekskill, about 60 kilometers north of Spectrum's offices here in New York. Bantam Tools is run by Brie Pettis of 3D printer company MakerBot fame, and who has actually written for Spectrum way in the past. Bantam Tools, though, focuses on CNC equipment, so the 555 kit is out of its scope. But fortunately, Solar Robotics in Calgary are continuing to sell and support this kit. The transistors in this kit and in the 555 are all bipolar junction transistors, the simplest type of transistor, and they come in two flavors, PNP and NPN. The voltage comparators use the PNP and NPN resistors in matched pairs, while the flip-flop uses just NPN resistors. Now it's time to clean up these resistor leads with my snips, so I've space to solder in more components. I always try to leave this as late in the process as I can, as mistakes are much more fixable if a component still has its complete lead. One nice detail about this kit is it has the orientation of the transistors printed on the board, making it a lot less likely that you'll make the common mistake of wiring a transistor in backwards. Time for a quick clean of my soldering iron with my trusty little can of Radio Shack brand tip, thinner and cleaner. I think you can still get this stuff even though Radio Shack stores have vanished from so many places, alas. These metal things look like pins, but they are just a decorative support for the printed circuit board. Actual electrical connections are made using the screw connectors on top. But honestly, these things are the fiddliest thing about this kit. It's one of those times where you need 3 hands to keep the screws and spacers in place while you hold the support in place and then try to turn a screwdriver. But the metal is nice. The first version of this kit used plastic legs, which snapped off pretty easy. Okay, now we're trying comparing the kit directly with a real 555 chip. This breadboard circuit uses some resistors and a capacitor to put the 555 into its astable oscillation mode, and you can see the output turning on and off the little red LED. If I swap in a capacitor with less capacitance, the oscillator runs faster. Now let me swap in one with even less capacitance and the LED actually blinks on and off too fast to see, but you can follow the 555's on-off output on this oscilloscope. Now let's pop out the 555 and wire in the kit. The output, as seen by the LED, looks about the same, but let's stick in the fast capacitor and take a look at the oscilloscope trace. You can see this is similar, but not identical to the real 555. But I think the difference here is due to the capacitance of the long wires I'm using to hook the kit up to the breadboard. When I tested the first version of this board for a hands-on column and spectrum using a more rigorous setup, I did get almost identical traces. With the completed kit, it's easy to see the different sub-circuits, such as the threshold and trigger comparators and the flip-flop. And there you have it, one gorgeous working giant 555 timer. That's it for this build, but check out our hands-on article about the kit on the Spectrum website for more, and I hope you'll join us for more kit builds in the future. For IEEE Spectrum Hands-On, I'm Stephen Cass.